Alright, what's up, guys? Welcome to day 13 of trying to become just a little bit smarter. I probably going to spend some time today going over, not to the host. So I have some things I want to look at. Yeah. So these are all problems or questions that I have for some basic stats concepts that I kind of need to refresh a little bit on in order for me to hopefully do well in my class. So I think what I'm going to try to do here is probably go through some slides from my school and then also create some flashcards that can help me throughout this process. Alright, so BUFN, portfolio management. Modules, let's see if simple portfolio theory. Yeah, wait. Okay, so I think these are some of the slides that we talk about here. Okay. Increasing. So PDF of a continuous random variable is simply the derivative of the cumulative distribution function. Intuitively, for a very small change in x, change in fx, x is equal to probability x is less than or equal to x, less than or equal to x plus change in x, which is equal to fx, x. Okay, that I did not know. Example, suppose x is, Okay, here's a 3-star important slide. Okay, let me also close my door. Okay, so let's take a look. For any constant c in an arbitrary function g, any constant c and arbitrary function g, what is the the expectation of c. So the expectation of a constant c, y, is equal to c. Okay, so because c isn't a random variable, it will always happen. So this is because c is not is a constant, and thus will always be the same value. Thus, when we find the expectation is equal to the value of the constant itself. This is because c is a constant and thus will always be the same value. Thus, we find the expectation, it is equal to the value of the constant itself. Okay, so what is, what is the expectation in stats? How would you describe? So y is the expectation of a constant. It's a quantity that always has the same value. Thus, if I understand, okay. So what is, for any constant c and arbitrary function g, what is the expectation of c dot g of x? So this is the expectation of a constant, so y. Yeah, if any function is the expectation of the output of any function. I guess it depends on what g is, right? So AC C dot G of X is equal to C times E of G of X. This is because of the fact that expectation of constant is equal to constant. So we can of one expectation and expectation C G of X is equal to the expectation of C dot the expectation of G of X. Okay, that didn't do anything. Expected value is linear. Okay, so let me think about it. When you're taking the expectation of something, I guess a very broad idea is, not Siri. Shoot. Okay, so a very broad idea is the fact that you're taking the weighted average. And so because the expectation is simply just a linear function, we can, I guess, treat the expectation as a function, so as a linear function. And I think from the properties of mathematics, if you have two numbers that are multiplying each other, it's the same thing Okay, so I think maybe this is the idea that fx y is equal to fx times fy. So what is the case of this? That means that f of x is equal to x and f of y is equal to y. So fx times y. I think this is like a general form. So this is saying that if you have function f and if you input the product of two variables x and y, that's exactly equal to the product of f of x and f of y. And so maybe this suggests that f of x is equal to x and f of y is equal to y. But with expectations, you have weights. So you have w1 x, and you have w2 y. Y is Oh wait, you know what? This might not actually be true because this is a constant itself, not another function. So this is a function. This is a constant. So I think C here is just scaling the actual function itself. So because of that, F2y's. So I think this has to do with something. So this is like f of 2y is equal to 2 times f of y. So I think that's what this is saying. Okay. So what is the linearity of expectation? So this is the idea that the expectation of the expectation of the sum of the expectation of the sum of a collection of random variables is simply the sum of the expectations. Okay, so this results in the following mathematical properties. Okay, so with this in mind, you have the so the expectation, I think, so you have the expectation of the sum, so he has it from I is equal to 1. Math BB big. Yeah. Okay. Sum of I is equal to 1. We have n of ci times gi, gi x big. So this is actually equal to the sum of I is equal to 1 of ci dot the expectation, so math BB gi So what does this mean? We have the expectation of the sum of a function of random variables is equal to the sum of the constants times the expectation of the function, where g of I is a function, c of I is a constant, x is a random variable. Real valued function. So what are its properties? What is an example? Example of this is so we have the expectation of a x plus by is equal to a expectation of x plus b times expectation of y. So we can split the expected values. Okay. So why is this true though? Why is the linearity expectation true? Using induction. Which is equal to, so this is a big thing here. We have x plus y's. 6 times x plus. Okay. Oh, sum of y. Okay. So I think. Right. So what is a basic proof for the linearity of expectations for discrete random variables? Start by showing that what the showing so expectation of x plus y is equal to the sum of x, y, x plus y dot probability of x is equal to x, y is equal to y, right? So I think this is kind of the first step into proof. So this is uses the definition of expectation of x and extends it to two RVs. So I think what would be helpful is we show that the expectation of x is simply equal to the probability of x is equal to x times x. So this is what the expectation is, in mathematical terms. X times P of x is equal to x. All right. Oh wait, this is the sum x, sum of all x. All right. So using 1, starting from 1, can distribute the x and y. So we have now 2 expectation of x plus y is we don't really need that. We could just do sum of x, sum of y, of x plus y, x p of x is equal to x, y is equal to y, plus y c dot p of x is equal to x, y is equal to y. Okay, right? So we have this. So we go through all of the y's. This is kind of like our a two. This is like a for loop, or a two-dimensional for loop. We're in a for loop. Okay. Okay, so from here, how do we get down to? So okay, so our goal is to show that the expectation sum x c dot, the probability of x is equal to x plus sum y of y c dot p y is equal to y. Okay, so this is, I think, our goal. Notice that equals expectation of x plus expectation of y. Voila. Okay. Starting from 1, 2, from 2 we can from 2, okay, we can, So I feel like there's a property we need here. So there's a addition within the summation. Yeah, I think we can split these two things, right? So can use the property of summations sum sigma. So it says so sum of x, sum of x plus y plus y is equal to sum of x plus sum of y. But we have to be careful about these. as xi, yi, sum of I. I think this is probably better. So yi. Oh, wait. Oh, okay. Yeah, that's good. So maybe this is the property. I'm trying to think here. So we have I iterations of xi plus yi. So there's the same number of x plus y. Right. So, okay, yeah, this should be true because I think what this is saying is we're adding up all the x's and then we add up all the y's. That's the exact same as just adding the pairs of x and y all together. Okay. So maybe I can... So 3 then, we have the sum of x, sum of y, of x, c dot, so probability of x, oh wait, yeah, this isn't good. So x, c dot x is equal to x, y is equal to y plus y I think this should be y. Okay, there we go. Yeah, this is pretty messy. Okay. We can use using the property. So I believe if we take the sum of I of, let's say, xi Oh, so this is the constant property. So yeah, no. So this is some constant times, say, xi c dot, where c is a constant. So this is actually equal to c times sum of I times xi. Okay. Because within this summation, x becomes a constant. I think within this summation, y is not a constant. But I think you can flip the two so that eventually, yeah. Using the property summation of I, c times xi is equal to c times sum. So we have 4, the sum of okay, maybe using the property. So I think sum, when we have two sum, say I x sum of y y so this is equal to sum of x y sum of sum of y sum of x y. Yeah, okay. And wait. Can write so all we have to do now is just swap the two. Yx. Oh shoot. Wait. Yx. Okay. 4. Alright, this should be 4. There we go. And this should be 5. Alright. X sum of y. So this is what we have. Using the property, so we have sum of y c dot y, actually probability of x y is equal to y. Y is equal to y. 1 plus Oh shit. yn. X. X. Okay, there we go. Six. I think this is good. So yx. Oh, but they use induction, which I kind of forgot how that's used in maths again. I didn't really learn about it that well in my proofs class, so maybe that's voila. How do we extend to n variables with induction? It's a good question. I don't know. Okay. We have integrals. Okay. Okay, so we have variance now. The variance. Oh wait, we got the chat. Let's see. Oh, yo, it's good. Yeah, I forgot it though. Most of it. Okay. Okay. The variance of random variable x measures how concentrated or dispersed the distribution of x is around its mean. That is, okay. How can we define the variance r of x? for any random variable x. So let's say variance of x is equal to the expectation of x minus the oh shit. Minus, we mathematically define. Okay, so it's the average squared deviation, I think. So, I see. Math DVs of x. Then we square this. Yeah. So this apparently turns out to this. This, how can we put this to words? So this is saying the variance is the expected value of the expected value of the squared deviation from the mean. So this is again the expected value. Okay, so I think this is the big picture here. So variance really mathematically in this form is just saying that it's the expectation of a random variable minus the average, or the expectation of a random variable. And we just square it. And so that'll give us kind of the dispersion of our sample, or maybe the dispersion of our random variable. The spread is another way of looking at that. Expected value of the squared deviations from the mean. Okay, so this is nice. Now we have variance of x is equal joint distribution, covariance property involving covariance. Wow, this is long. Law of iterated expectation. Unconditional independence. Proportional properties of summations. Oh, this is a covariance matrix. Never mind. Bivariate normal distributions. Okay. Variance. Okay, wait. So how would do we get from, so variance of x equal slash e math bb of x minus, oops, okay, yeah, here we go. So how do we get from this to math bb expectation of x squared minus the expectation, yeah, expectation squared. Okay, yeah, how do we get from here, which is a big step, oh shoot, I'm missing a parentheses here, yeah, so this is a big step, oh man, you know what, I think, there we go, that's probably better, okay. So let's see, I remember our stats teacher talking about this, gonna be on, Allison, hello Allison. Okay. Hey, shout out Allison. Shout out my boy Andre. 2 concurrent viewers at the same time. That is crazy. I've never had that happen before. So thank you. Andre, we still gotta stream, bro. Come on. Okay. So let's see what we're working with here. Let's start with what we know. Alright, we know that the variance of the expectation of x okay, can we can we break this down a little bit further? Let's start, so starting from the initial definition, so this is going to be expectation, the final definition. Okay. So what are the properties of the expectation? We saw that it was linear, so if we you know what, I don't think these parentheses are matching up with what I think they should be. this is what this should be. Okay, I think this is the right way to think about it. Great, so I think what we can do here is we could probably distribute this, right? So this is we can factor the term x. I don't know if factor is the right word. Maybe expand the term so then this gives us x so then this gives us 2 math the expectation of we have all right, okay. So I think from here then, to all right, so that's just the properties of an exponent. Okay, and then I think what we could say here is we multiply this by that x times the expectation of x. Then distributes the terms. So we have math BB. So we have expectation of. So we have x squared, and then we minus. Yeah. Yeah. Expectation of.
I know you've been doing some streaming and studying. I gotta give you some motivation right here.
Oh my god.
There's like 5 slides.
Before age 25, get in the habit of doing these 3 things for 60 minutes each day. 60 minutes of fierce edge. Alright, I gotta stop talking out loud. 60 minutes of Mongolian throat singing.
Have you heard that? It's so funny.
60 minutes of spreading misinformation online. 60 minutes of committing tax fraud. 60 minutes of aggressive deforestation. Jeez. A woman once asked me what my favorite position is. I said CEO. She said sexual obsession. I said CEO. No matter what I'm doing, oh, just CEO. And I never answered.
Read that again.
Yeah, read that again. Back in the 1900s, becoming a millionaire was an impressive feat. Nowadays, being a millionaire is one small step from being away from poverty. If your goal is to become a billionaire before 40, this should be a stand for everyone. Oh yeah. You this weekend, alcohol, closed bars and drinks. You this weekend, burning fossil fuels. Learning to Mongolian throat sing and tipping my landlord.
Dude, Mongolian throat singing is so funny.
I need to look that up later. But I feel motivated.
You feel motivated?
Yeah.
I'm good for the 10:15 run, by the way.
10:50 run? Let's go. I gotta go use the bathroom.
Well, really.
Start jerking off. And there's a man, screaming, kids were crying, everyone had their phones out. Whites, blacks, Latinos, you know what it is. The action shooters was begging me to stop. But yeah, the pilot had no choice but to make an emergency landing in, you guessed it, Denver, Colorado. Sure, expecting that in jail. Now I'm on some stupid fucking list, but I saved $142 on my flight. There's always a better deal. Always.
Yeah, honestly, fine. If it's cheaper to go further that way, when you get over the area you're at jerking off, they do an emergency landing, you're over there.
Yeah, man.
I don't see anything wrong with that, right?
Nah, alright. I still need to call these guys. Get this shit fixed. I need to call.
blue? Yeah, for sure.
I need to do that.
Probably just put in a work order, right?
Yeah, I gotta.
I mean, again, it shouldn't be hard. They probably just take the floorboard out, redo the glue there, clean it, and just put it back. Because it's only that one floorboard. All the other one, it's this one. Is it still seeping out? Yeah. Honestly, should we put like some napkins there so we don't have to step there? Because every time we step there, it seeps out a bit more. I mean, look how much there is on the side now. Should we just put a napkin there so we don't have to step on it?
Okay.
Go to the bathroom, I'll do it. Oh, we can actually just do this.
I'll take a look, babe.
You can just put the paper towels over it. Like the paper towel plastic thing over it. Like we have like the thing of paper towels. We can just put it over the floorboard. Nice stream. It's cold outside, by the way. I'll do it. I gotta get better. Gotta get better. This is how I earn going back to the gym.
Yeah.
Right?
It's gonna be nice.
I woke up at 4. I heard those
Right,
birds
see.
singing, and I knew I was behind. I woke up at 3. But like this, just straight, just flat.
Okay, let's do it.
Just do that. That's fine. Is that? Well, don't put it on the side then.
This is probably good.
Well, don't want to cover the glue.
Right here.
You see that?
Then it's just an obstruction.
Yeah, it should be. The glue is an obstruction anyway.
Okay. We'll leave it there for now.
Do you actually have like work yet, or is this more personal stuff?
What personal stuff?
I gotta say, it's not, dude. Beginning of semester is so nice. I got nothing to do. It's such a difference from like November last semester. Every time I would come home, everyone's just in the room doing whatever the fuck they need to actually do.
Yeah. I'm glad. Now it's just you can stress about whatever.
What do you want for your birthday?
I just want some wings, man.
I'm giving you something for your birthday. Is Josh's birthday in spring or did it already happen?
Because that was in October.
That's the thing. Because I'll get him something too, because I forgot. But like, I vaguely remember freshman year, I went to get lunch with him, like sometime in spring, because he only came in the spring to campus.
Yeah.
And he said it was his birthday then. I vaguely remember that. But I also then remembered this year, he said it was his birthday in like October or November. So like,
Yeah.
I don't know.
Okay.
I forgot to get, I'll get him something.
Or we could just go to MGM, just have a good time. That could also
I'll
be,
get him a gambling addiction for
that could also be a good gift.
I'll get you a gambling addiction for your birthday. How about that?
Just it's the experience that matters, not the gift. Oh my god.
I take you to a casino and you're like, yeah, it's a great fucking birthday. I'm literally 50,000 in debt for your birthday. That's my gift. I'm giving you the grind.
The grind. Oh my god, it's the best gift a man can get.
Exactly. I think Royce could have one of those like People say it's good to have a head start. I disagree. How are you going to overcome adversity without adversity? When I graduated college, I tore up my diploma, ripped down my house, and like started screaming,
Yeah.
just so I could come from the fucking bottom. And look where I am now. I'm crippling heroin addiction and like something else. But at least I didn't have a fucking head start. It's like that. It's like the motivation one, like the
Royce
I
DuPont.
think Entrepreneur is actually the best TikTok account. It's also the other guy who like. is,
The podcast? Is
yeah,
it that guy?
The fucking podcast guy where it's like every Friday I organize a pizza party in my break room. The thing
Oh, yeah.
pops up like my off like there is no break room or
Uh-huh.
Wi-Fi. It's like, and anyone who shows up and says where's the pizza party,
Yeah.
I give them a job application to Domino's. There's your fucking pizza party.
Jesus Christ.
When you like make your business, I need you to run it like that.
Okay.
Oh, bit of an issue. There's some glue here. There's
Oh.
another forward. Right. That is glue, right?
Yeah, it looks like it. I don't. That's that funny.
I'm not. I'm just wondering. I mean, there definitely can't be. I know we haven't really cleaned these things yet, but that still can't be our fault that the floor was literally coming up.
Oh yeah, I think that has to do with the glue. It's probably because.
Oh my! Oh, the glue stuck. That's dry glue from before.
Yeah. Not too sure.
I mean, even if they put, is this something? We can ask a work order just to make sure that the floorboards are like actually like set down,
Yeah, yeah.
and like we can let them know like we'll clean like the dried stuff because I guess we probably should have done that from before.
Uh-huh.
But like the initial glue thing, like that needs to be fixed. Like that's
Right,
not
right.
on us. Like we don't know how to fucking. If it's coming up, I don't know how to put it back.
Yeah, okay, that's fair, that's fair.
Unless you want to learn how. I'd rather not. I
Yeah.
have too much grinding to do right now.
Yeah, me too. Okay, we can distribute the terms.
Probably two or smart. Right?
Close this for now. Okay, so if we distribute the terms. Okay, I'm not too sure if this is going anywhere, but let's see. So then we distribute the terms. Simplify. Two times x, expectation of x. Hmm. Yeah, I feel like this might not be the right way. Let's do some calculation wrong here. So we have x minus the expectation of x, and then so we have our initial definition here. Right, so maybe this x minus, so x times x is x squared. X times negative expected value of x. So x times the expected value of x, right? Negative x times x is x times negative. Ah, man. To x minus expectation of x, wait, x times x, expectation of x squared minus x ex minus 2 times x. Okay, yeah, I'm kind of stuck here. So what do we know about the expectation? Again, it's linear, so expectation of x plus expectation of y. Expectation of x plus the expectation of y. What about the expectation of the product of two different variables? I feel like this has something here where if you have x minus expectation of x square x times x is x squared minus x times expectation of x minus x plus e to the x squared. So if you take the expectation of this, expectation of this, expectation of x of okay, so the expectation of an expectation is just equal to that, right? Using the property at the EB. So the expectation of x is equal to the expectation of x. Okay, so this is just saying that, right, because the expectation of x is a real value, and so that should be a constant. Okay, maybe that this only changes if x changes. So I think, so c is a constant and never changes, right? Expectation of x is a real value that does change. So is the expectation of x a random variable? Let's see. Expectation of a random variable itself. So measure now. Simple space. Vibrant. Risky case. So what is the expectation of an expectation? Okay, so I think I was on the right track. Okay, right. Ah, so I was going in the right track. Then it distributes the term, the x. Okay, so I think this is using the linearity of expected values. We can do the. Okay, so using the linearity of expected values, we can compute, what's it called? Using the linearity of expected values, we can move, take the expectation of each term. Okay. So 5 math BB. So the expectation of x squared minus the expectation of e times, so expectation of x math b e to the, oh shoot, e to the x times math BB, so e to the x, okay, plus, so we need e to the x. to the x squared. The expectation of the expectation. Oh, man, there's so many e's in this damn equation. All right. There we go. 2 times c dot. Two c dot. 2 c dot. Expectation of the expectation of x squared. Okay, so what is this? Expected value of x times the expected value of x. So there's gotta be a way we can look. There's gotta be a way we could look at the expected value of x times expected value of x. Okay, so expected. This is product. Okay, oh man. Why is this so hard? Why is math so hard? I'm a senior in college and I still can't grasp this stuff, but hey, that's why we're here. So my mind's not working. But if we have, okay, if we're taking the product between these two, x times the expectation of x, find the expectation of that. We need this to be 0, right? If we want to get to, oh wait, no. Oh, okay. I kind of see where we're going here. So I think what this is saying, it's the okay, wait, let's kind of split this up here. So I think what we can claim here is that expectation of x k times the expectation of x. So I think this is equal to the expectation of e to the x. Okay, so expectation of x times the expectation of the expectation of x. Oh my god, that is crazy. Okay. Oh my god. Yeah, there we go. God damn. All right, there is a lot of expectations here. There's a lot of e's, so let's split that up. Okay, and then this is equal to the expectation of x times the expectation of x. Oh shoot. Which is equal to the expectation of x squared. Okay, using the following properties. So I think A and B okay. Now what we could see is that the expectation of x squared minus 2 times the expectation of x squared, so plus the expectation of x. Okay, now this is looking pretty good. We can arrive at the following. So the final when we we can subtract the element, we can subtract and get the following. So variance of x is equal to expectation of x squared minus expectation of x squared. Alright, so what is this property? Okay. I think we need a note. Note that we okay, wait, what is the expectation of expectation? Okay, so expectation of x is a number. So I think we should actually swap this. This should be the first. Yeah, this should be the first definition, and this is the second. Okay, nice. This is okay, so this I think is the final kind of mathematical jargon that we need to get from the expected value of the square deviations to this weird formula using the expected value of x squared minus expected value of x squared. And so what happens is we can start with the initial definition we have here. And you notice that there's a square in the exponent, or a 2 in the exponent. And so just expanding that term out, we'll get something that looks like this. So, well, we can replace this term, number 1, with expectation of x minus the expectation of x. And we just have that twice. One here and one here. Okay, and then when we have something that resembles this form, I don't know what it's called mathematically, but we can distribute the terms so that we multiply x to x, x to negative x, to x to negative ex. And then we do the same here and here. So we distribute the terms. It's math. Let's see, it's distributing and math. Okay, this is it's just a law, I guess. Is the distributive property an axiom? Among the axiom for rings, like the ring fields. The axioms are in starting point. Okay, these guys are getting into an argument that I don't really fully understand, so I'm going to skip that for now. I think I might get too deep into the weeds. But okay, I guess I'll just take it at face value when you're multiplying something of this form. So this you can think of as a single number, and then this you can think of as the same number. And in order to multiply these two numbers, what we can do is break it up into the differences of two different numbers and then multiply each of those together. Okay, so now we have something that looks like this. And this is where I really got stuck, actually this part, because I didn't really know where to go from here. I didn't fully understand yet that when you have the expectation out here, what you can really do is take the expectation of an expectation, and that'll just give you the actual expectation itself. So you can treat as e of x as just ex. And the reason is because the ex is just a number. And in this form right here, we have three different, so I guess you could call random variables or constants. And that's where we can use the linearity of expected values to be able to transfer something that looks like this to something that looks like this. So we've pretty much taken the expected value of all of these random variables and all of these constants. Okay, and then this is kind of where we had to make that kind of epiphany that if you take the expected value of an expected value, it just gives you the expected value. And that's a really nice property that can help us get to something that is more meaningful. So we can take this right here, and what we know about this is we can treat ex as a constant because we know that's from property A, and then we have a random variable here. And so what we do here is we could say that ex times ex is equal to ex times ex, and that's equal to e to the x times ex, which is equal to ex squared. So now we have something that looks like this. So this is a law that we saw earlier, like e to the constant times x is just equal to e to the x times is just equal to c times e to the x. So what is the expectation of xy? So it's possible for exy is equal even though x and y. I see. So this delves into a much more harder topic of joint distributions that I don't think I'm fully ready for yet as of today. So I think what we have here is pretty sufficient. So we arrive at the following, we subtract and get the following. Okay, so I like this. This is very nice. All right. The variance of a constant is 0. Okay, yeah, that makes sense because expectation of a constant squared is just equal to the constant, and then this is also equal to the constant squared, so that's just equal to 0. Times g to the x. Okay. Alright, I think I'm gonna go for a run right now, but we made some pretty good progress with variance and expected values. I think these properties are very helpful. Maybe I can pick up on covariance later, but I'm not too sure if I'm going to do that or maybe work on some Zing fun stuff. So I'll get back to you. But I'm going to end the stream right now. Thanks for watching. Made some progress. And that's it. That's it. All right.